All right, let's finish up the material for exam 1. And in chapter 2.5, we're going to be talking about measures of position. All right, so in a broad kind of description, fractals are numbers that partition or divide an ordered data set into equal parts. Now, that's not really something you need to be concerned with, other than just know that there's different types of fractiles that we're going to be talking about. The first, and probably the most important one that we'll use, are called quartiles. Quartiles approximately divide an ordered data set into 4 equal parts. There's the first quartile, Q1, which is about 1/4 of the data, all right, it falls on or below Q1. All right, and the second quartile, Q2, this is always going to be the median, you guys. Q2, second quartile, and the median are the same thing because it represents about 1/2 of the data, all right, that falls on or below it. And then the third quartile, Q3, well, that's about 3/4 of the data fall on or below Q3. All right, so let's go through an example of finding our quartiles. The number of nuclear power plants in the top 15 nuclear power producing countries in the world are listed. We want to find the first, second, and third quartiles. All right, first let's get Q2. Q2 divides the data into 2 halves. All right, notice step 1, we have to order our data. So we order it from the minimum of 6 up to the maximum of 104. All right, with this data, since there's 15, we know the middle number is going to be our median. So 18 is our median or second quartile. This gives us a lower half and an upper half. All right, so here we're going to find our quartiles. We've got our median of 18. All right, so how are we going to go about finding Q1 and Q3? Well, guys, it's pretty easy. They're just the medians of the lower half and upper half. All right, so looking at our lower half, our number 6 through 17, we need to find the median of those 7 numbers. Well, that's easy. We can see it's 10, the middle number, so Q1 is going to be 10. All right, in other words, about 1/4 of the countries have 10 or fewer nuclear power plants. All right, now let's do the same for the upper half. All right, we have our upper half of data, 18 through 104. We're looking for the median here, and the median is the middle number, or 31. And so Q3 corresponds to 31. About 3/4 of the countries have 31 or fewer nuclear power plants. All right, let's talk about the interquartile range, oftentimes abbreviated IQR. This is just going to be the difference between the third and first quartiles. So it's kind of like the range where you subtract the maximum and the minimum, but here for the interquartile range, you subtract the third quartile with the first quartile. All right, so going back to the nuclear power plant data, we've already found that Q1 is 10, the median is 18, or Q2 is 18, and the third quartile is 31. So if we want the interquartile range, we're just going to subtract Q3 from Q1, or 31 from 10, and we get 21. So the number of power plants in the middle portion of the data set vary at most by 21. All right, let's talk about how we're going to do a box and whisker plot. All right, so, the box and whisker plot's actually pretty helpful. It highlights important features of a data set, all right, and because it requires a 5-number summary. So when we get a box and whiskers plot, or rather when we make one, we're going to be able to quickly see the minimum, the first quartile, the median, the third quartile, and the maximum. It's also going to give us an idea of how our data is distributed. All right, so when we're drawing a box and whisker plot, the first thing we have to do is find that 5-number summary of the data set. Then we're going to construct a horizontal scale that spans the range of the data. In other words, this horizontal scale will go from the minimum up to the maximum. Then we're going to plot the 5 numbers above the horizontal scale. And then we're going to draw a box above the horizontal scale from Q1 to Q3 and draw a vertical line in the box at Q2. All right, so why are we doing this? Let's take a look at our picture here, guys. We can see on the horizontal scale, we're going from our minimum to our maximum. All right, then we see the interquartile range from Q1 to Q3 very visibly. And we see where the median falls in comparison to Q1 and Q3. All right, and we have our whiskers here. So we're able to see, is the minimum or maximum, are they huge outliers? You know, how does the median fall in relation to Q1 and Q3 and so forth? Okay, and then lastly, yes, we draw those whiskers from the box to the minimum and maximum entries. All right, so let's go through it. All right, we want to draw a Box-and-Whisker plot that represents the data set. All right, so this is our nuclear power plant data. We know our minimum is 6. All right, so starting out, we plot 6, we plot 104. All right, we then plot our Q1, which is 10, our median 18, and our Q3, which is 31. We draw our box around Q1 and Q3. We draw our line at the median. All right, and so what do we see when we look at this? That 104 is pretty darn crazy, isn't it? All right, so about half the data values are between 10 and 31. By looking at the length of the right whisker, we can conclude that 104 is a possible outlier. Do we know for sure it's an outlier? No, because we have to quantify that with standard deviations, but it sure does look like one. All right, let's also talk about percentiles and deciles. I'm just going to mention deciles. We're not really going to do them. These divide a data set into 10 equal parts. And then we have percentiles, which we've all heard of, especially when it comes to taking the ACT or the SAT. Percentiles divide a data set into 100 equal parts. And look, before I go forward, let me just remind you, it's easy with quartiles to remember that Q1 means a quarter of the data is below this. And with Q2, half the data is below. And Q3, 75% is below. Keep that in mind when you're working with percentiles, that P3 means 3% of the data is below. 99 means 99% of the data is below, okay? All right, let's talk about interpreting percentiles. The graph represents the cumulative frequency distribution for SAT test scores of college-bound students in a recent year. What test score represents the 62nd percentile? All right, and how should we go about interpreting this? Well, first of all, let's try to find the 62nd percentile. All right, so we can see that the 62nd percentile corresponds to this SAT score, which happens to be 1600. All right, this is obviously including the writing portion, guys. All right, so the 62nd percentile corresponds to the test score of 1600. How do we interpret that? That means that 62% of the students had an SAT score of 1600 or less. Okay, so 62% had that score or less. All right, let's talk a little bit about z-scores, or oftentimes called standard scores. Z-scores represent the number of standard deviations a given value x falls from the mean mu. All right, so again, a z-score is just telling us the standard deviations. All right, the standard deviation for a certain data value from the mean. All right, how do we go about calculating a z-score? Well, it's just going to be the data value x minus the mean mu divided by the standard deviation. All right, let's take a look at an example. In 2009, Heath Ledger won the Oscar for Best Supporting Actor at age 29 for his role in the movie The Dark Knight. Penelope Cruz won the Oscar for Best Supporting Actress at age 34 for her role in Vicky Cristina Barcelona. The mean age of all Best Supporting Actor winners is 49.5, with a standard deviation of 13.8, right? So mean of 49.5, this is our mu, and a standard deviation of 13.8, this is our sigma, all right? The mean age of all Best Supporting Actress winners is 39.9 with a standard deviation of 14. So this is our mu for the females, and I should do a subscript here for males. So 49.5 is the mean for males, all right, and 39.9 is the mean for females. And then we have a standard deviation of 14. So this is the sigma for the actresses or the females. And then the 13.8 was the standard deviation for the males. Let's find the z-scores that correspond to the ages of Heath Ledger and Penelope Cruz and then compare the results. Okay, so Heath Ledger, his age is 29, or was 29, minus the average age, all right, for Best Supporting Actor winners, and we're dividing that by the standard deviation for Best Supporting Actors, the 13.8. What do we get? Negative 1.49. So Heath Ledger's age in comparison to other winners was 1.49 standard deviations below the mean. What about Penelope Cruz? Well, her age was 34 when she won, and the average age for Best Supporting Actresses is 39.9. So we get that difference and divide by the standard deviation of 14. And what do we find? Well, we get a z-score of negative 0.42. What's this telling us? It's telling us that Penelope Cruz's age when she won was 0.42 standard deviations below the mean. So how do we interpret this? Well, both z-scores fall between negative 2 and 2, so neither score should be considered unusual. Compared with other Best Supporting Actor winners, Heath Ledger was relatively younger, whereas the age of Penelope Cruz was only slightly lower than the average age of other Best Supporting Actress winners. All right, so in other words, Heath Ledger's age when he won was roughly about here, negative 1.5, whereas Penelope Cruz's age was roughly there in terms of standard deviations from the mean. All right, so you can see that Heath Ledger's further from the mean, his z-score was more negative, and so he is in comparison younger when he won compared to Penelope Cruz.